acid. So now we're going to go on to talk about the production of ethanol and biodiesel. So first of all, we're going to look at the production of biodiesel. So biodiesel is the process of producing what we otherwise know as biofuel or biodiesel through the chemical reactions of either transesterification and esterification. So this can either be done by using vegetable or animal fats and oils and reacting these with short chain alcohols. So short chain alcohols being something like methanol or ethanol. Typically, this will be no longer than ethanol. And so the alcohols should be of a very low molecular weight. So ethanol is typically the most commonly used one because it's of low cost. However, greater conversions can be achieved if we're to use methanol for this particular reaction. So there is that conflict between choosing methanol and choosing ethanol. However, ethanol is typically used as it is more low cost. And so the transesterification reaction can be catalyzed through either acids or bases, whereas we have a base catalyzed reaction, which is our most common version. And so that's because the base catalyzed reaction has a lower reaction time, and the catalyst cost is going to be lower for the base catalyzed version as well, compared to those of acid catalysis. However, there are some disadvantages of using the base catalyzed process, and so that's because alkaline catalysis has high sensitivity to both water and also any free fatty acids which are present in the oils. And so in our base catalyzed method, we'll typically use a base such as sodium hydroxide, so NaOH, and so that will help us to catalyze this reaction. And so common feedstocks which are used in the biodiesel production include what we know as yellow grease, so that's like a recycled vegetable oil, then just like other vegetable oils, and tallow may also be used. And so the recycled oil then gets processed to remove any impurities or any like burnt parts from cooking, storage, handling, etc. And basically just make sure that there's no impurities such as dirt or water in there. And so then this is refined and the phospholipids and any other plant matters are removed through refinement processes. And then water is also removed as well because during the base catalyzed transesterification reaction, as we mentioned before, this would result in saponification, which is the process of making soap. And so that's a hydrolysis reaction of triglycerides, and that's also base catalyzed process. So if we were to put triglycerides and water together with the sodium hydroxide, we would accidentally produce soap and glycerol instead of producing the biodiesel and glycerol. And so that would obviously not be the process which we are wanting. And so a sample of the clean feedstock also is tested via titration against a standardized base solution to determine the concentration of free fatty acids which are present in the vegetable oil. And so these acids are then removed typically through a neutralization reaction or are esterified in order to produce biodiesel or glycerides. And so we can see on this the reactions which we use as shown on the screen here. We've got the base catalyzed reaction and the acid catalyzed reaction would undergo the same process. So we start off with our triglyceride, which is a 3-chain molecule connected through this carbon backbone, and we add that to a ratio of 1:3 of either methanol or ethanol. And then we combine that with our catalyst, which is sodium hydroxide, typically in our base catalyzed method, and that will produce 3 fatty esters, which are the biodiesel, and glycerol, which is our byproduct. And so these typically are going to produce biodiesel and our impure co-product, which is glycerol. And so if this has a high acid content, the acid catalyzed esterification can be used to react the fatty acids with the alcohol to use biodiesel. But we can also use other methods such as fixed bed reactors, supercritical reactors, or ultrasonic reactors to forego or decrease the use of catalysts, so that base catalyzed or acid catalyzed method, but we won't discuss those methods today. We also have the lipase catalyzed method, but the lipase catalyzed method is not used as commonly, but often there has been large amounts of research focused into this because it uses enzymes as a catalyst for the transesterification reaction. And so researchers have found that very good yields can be attained from using from crude and using oils with lipases. And so the use of lipases, which are an enzyme which breaks down fats, can make the reaction less sensitive to high free fatty acid content and water as well, which is a problem with the standard biodiesel process. So one problem with the lipase reaction though is that methanol cannot be used because it will inactivate the lipase catalyst after only one batch. However, if methyl acetate is used instead of methanol, the lipase is not inactivated and so can then be used for several batches, which makes the lipase system a lot more cost effective. And so now we're just going to talk a little bit about what biodiesel is in terms of why it's used. So basically it is an investigated alternative for providing a carbon neutral fuel source for powering vehicles. And so basically it's using recycled feedstocks and no longer used oils to then go on to produce a fuel which can be used to power rail engines, cars, and factories. However, it does have its issues in that it can easily clog fuel filters and it's hard to purify. It's also not completely green as it's also producing atmospheric carbon, but it's just not using oils that are being pulled out of the ground, instead using recycled oils. So although it does have its upsides, it does have its downsides as well. And in addition to this, it is quite expensive to produce, so the process does require further refining. So now we're going to talk about the process of producing ethanol. So for producing ethanol, we have two main processes. Our first one, which we're going to look at, is called the hydration of ethene. So the hydration of alkenes is something which you've already looked at before in your organic chemistry topics. And so the hydration of alkenes can be applied to then making ethanol in an industrial application on a larger scale. And then we'll also look at the fermentation process to compare their similarities and differences. So the manufacturing of ethanol from ethene is used with steam and basically using a solid silicon dioxide catalyst which is coated with phosphoric acid. And so this is a reversible reaction, so we can apply Le Chatelier's principles to this concept, and it is done by we can then also remove ethanol from the system in order to also increase that reaction. And so when the gases from the reactor are actually cooled, the excess steam gets condensed and is then condensed with the ethanol, and then the ethanol gets separated through distillation to then separate the ethanol from the water to create then the pure ethanol. So the conditions for this reaction, we need to first of all consider the proportions of ethene and steam. So The equation shows that ethene and water react in a 1-to-1 ratio. And so in order to get this ratio, you would have to use basically just equal volumes of the two gases. Because water is cheap, it would seem sensible to use an excess of steam in order to move the position of equilibrium to the right, because according to Le Chatelier's principle, if you add more reactant, you're going to produce more product by forcing the reaction in the forward direction. But in practice, an excess of ethene is actually used. And so this is very surprising at first thought, because even if the reaction is going one way, you couldn't possibly convert all of the ethene into ethanol, and because there just still isn't enough steam to react with it. But the reason for this strangeness is that it lies within the nature of the catalyst. And so that's because we're using that phosphoric acid catalyst, which is coated onto a solid silicon dioxide support. And so if you use too much steam, it dilutes the catalyst and it can even wash it off. So it basically then just makes the catalyst useless, and hence obviously not increasing the rate or the yield of the reaction at all. So next we need to consider the temperature for the reaction. And so again, with the temperature for the reaction, we need to consider both equilibrium considerations, but also rate considerations. So when considering the equilibrium considerations, we want to shift the position of equilibrium as far possible to the right in order to produce the maximum possible amount of ethanol in the equilibrium mixture. And so this is because the forward reaction of this is going to be exothermic. So we know with exothermic reactions, heat is produced from the reaction, and so we treat heat like it is a product. So according to Le Chatelier's principle, if we were to increase the temperature, we would favor reactants. If we were to decrease the temperature, we would favor the products. And so we want to favor the products, so we should decrease the temperature in order to produce more heat by counteracting the system and then giving us as much ethanol as possible. So we want to use as low of a temperature as possible for this reaction. However, you can see on the screen here we're using a 300 degrees Celsius for this reaction. And so yet again, like we've spoken about previously, 300 degrees Celsius isn't a particularly low temperature. However, we know that the lower the temperature you use, the slower the rate of the reaction becomes. And so we know if the manufacturer is trying to make as much ethanol as possible per day, it makes no sense to try and achieve an equilibrium mixture that contains a very high proportion of ethanol if it's going to take a very long time to produce that. So we come up with our compromise where we then use the 300 degrees Celsius in order for the gases to then achieve equilibrium. And so under these conditions, about 5% of the ethene reacts to give ethanol at each pass of the catalyst. So we can see that that's a fairly ineffective method, but it's the best they can sort of get out of this method. So next we need to consider the pressure for this reaction. So you can notice that there are 2 molecules on the left-hand side of the reaction, but only 1 on the right. And so this is because according to Le Chatelier's principle, if you increase the pressure of the system, it will respond by favoring the reaction which produces fewer molecules, and so then obviously causing the pressure to fall again. And so in order to get as much ethanol as possible in the equilibrium system, you need as high pressure as possible, because we know that high pressures will favor that forward reaction. We also know that high pressures increase the rate of reaction due to their relation with temperature and the ideal gas laws. However, the pressure that we use for this reaction we can see is 60 atmospheres, and that's not a very high pressure. And so that's because there's 2 separate problems with this. So first of all, it's that the high pressures are expensive, and so it's going to cost more to build the original plant if you use extremely strong pipes and containment vessels, and it also uses a lot of energy to produce those high pressures, which would make the ethanol very uneconomic to produce considering we talked about before that there's only a 5% conversion rate of this reaction. We also need to consider that at very high pressures, ethene polymerizes, which means that it makes a very, very long chain molecule, which is called polyethene, which you may have heard of. And so apart from wasting the ethene, which could be made into ethanol, it's also clogging up the plant with these big solid masses, which are not producing what wants to be produced, and hence is just making a mess and actually could cause damage to the plant. Finally, we need to consider the catalyst. So there's the rate considerations for this catalyst. So in the absence of a catalyst in this reaction, it would be so virtually slow that no reaction would occur in a sensible amount of time. And so this is because we're trying to react ethene with water, and we know ethene is a very unreactive molecule as it is a type of alkene. It is purely just made up of carbon bonded to hydrogen, so that's quite unreactive. We know water is also fairly unreactive, so we do need that phosphoric acid catalyst in order to then ensure that the dynamic equilibrium can be set up within a short amount of time so that the gases are actually reacted in the reactor. And so other alcohols can also be made from other different alkenes, but in the case of this, we're purely just looking at the hydration of ethene. And so that summarizes the process of the hydration of ethene. We now want to look at ethanol though, produced by fermentation. And so ethanol by fermentation is only going to apply to ethanol. So unlike the process which we just looked at before, you can only make ethanol with this process, no other alcohols. And so the starting process varies widely for this, but typically it's going to start off with some sort of starchy plant material, typically like corn, wheat, barley, potatoes. And basically it's using complex carbohydrates to break them down into, so like our polysaccharides, to break them down into glucose. So we can see that's our first step here of the process, where we're breaking down this complex polysaccharide into glucose. And so you don't need to worry about remembering that part of the process. That's just to show that we're starting off with something more complex in order to use it to make this glucose. And so this uses enzymes just to break it down into simpler parts. And so what happens in this reaction is this part of the reaction is what you do need to remember, is the part at the bottom. But basically ethanol via fermentation is the process in which we convert glucose to ethanol and carbon dioxide by fermenting it in what we see here in this kind of type setup. And so a few important notes which we need to make about this is that the pH of the water which we are performing this reaction in needs to be neutral so that the yeast catalyst which we use, which is going to be enzymes, are not denatured. And so yeast is going to be, or any other microscopic organism that does fermentation processes, needs to be present and contain the necessary enzymes in order to catalyze this reaction. Another important point is that this must occur at low oxygen concentration. And so this is because oxygen will prevent fermentation from occurring, and yeast acts in low oxygen environments. So we need to ensure that it's closed off from high oxygen amounts. We also need to have glucose or any other similar type reactants for the yeast to break down to also use as energy in order to catalyze the reaction. We also need warm-ish temperatures, so like around 37 degrees Celsius, depending on the yeast or catalyst which is used. But it would typically be around 37 degrees Celsius, which is our body temperature, because that's the rate at which many organic enzymatic reactions occur, because that's in the enzymes, in like the enzyme's ideal sort of temperatures and its ideal reaction range. And so the alcohol produced from this type of reaction will actually only reach a concentration of about 14%. So in order to then achieve a higher concentration than this, you've got to then distill the alcohol. So we can see in this diagram here, the reaction occurs and then we put it through the condenser to then distill it into our graduated cylinder down the bottom here. So that's the process of producing ethanol via fermentation. And so when we can produce ethanol via either hydration or fermentation, we can then come to the conclusion that producing ethanol via hydration is often our more efficient process and is a lot more effective just overall in terms of its rate of reaction. However, ethanol via fermentation is going to be a lot greener compared to hydration. And so even though ethanol by fermentation is typically not used as it occurs so slowly, there is research into looking at improving its method.